Hi, my name is Izzy, and this summer I researched enhancing and developing the controls of a bi-copter drone. Drones are one of the most advanced machines being developed in the world right now. Most people don't know this, but aerial technology has reached heights never seen before. Pun not intended. When you think of a drone, most likely a quadcopter comes to mind. However, with growing use of drones in fields like agriculture and search and rescue, the need for a more efficient and compact model of the drone has never been higher. This is why the IDCL bi-copter, Benny, was created. As a third prototype, Benny the bi-copter was designed to fly with virtually half the weight and consume half the energy of a traditional bi-copter. All aircrafts follow three maneuverable dimensions: pitch, yaw, and roll. With the quadcopter, you have a symmetrical aircraft, virtually shaped like a square, with an even amount of rotors across its weight. However, with the bicopter, while symmetrical, acts more like a line than it does a square. It is unable to control itself on the pitch and yaw axis without servo motors being placed directly on its pitch axis. But here was the problem with this bicopter. It utilized SG90 servo motors to control its pitch and yaw. But these servos weren't responding well. There was constant jittering and instability in its pitch axis, which essentially would prevent Benny the bicopter from achieving controlled flight. So this begged the question, what about the SG90 servo motor, or any servo motor's behavior, points to flaws in its technical performance, especially when there isn't actually any existing documentation on it? In addition, by exploring the behavior of these servos, could it be possible to use what is known to produce a flight-ready model of the bicopter drone? These are the questions that became the major objectives of this research project. My main method of approach with this research was understanding how to characterize the behavior of servo motors. I had to know what the servo was being told and what it was actually doing. But the only way to do that was by isolating the servo motor, separately from the bicopter, and use a potentiometer as a physical sensor. Because there existed no pre-existing documentation on positional servo motor testing, I had to design something that hadn't been created before. An apparatus designed in CAD that could house a motor and a potentiometer on the other end. But all of this hardware was meaningless, unless I had a way to test it, which is why I used an Arduino Uno R3 board to digitally control the servo motors and get analog readings on the positional movement of the potentiometer. I designed two main test profiles. First, a frequency response test to test a servo at various operating frequencies and determine its response across those frequencies. I did this by collecting data in Python. After that, I would take that data and use a separate Python program to generate a Bode plot, which revealed the servo motor's variation in response to different frequencies. Essentially, what frequencies the motor can keep up with. The second test I designed was a step test, to check the response of the servo to sudden commands with large and small leaps in amplitude. And it gave me a very important lesson as a researcher about the significance of data collection in these specific contexts. Specific tests results in specific results, which results in more informed iterations. The results showed that these servo motors could not sustain the weight and response the bicopter drone demanded. In addition, with specific results from the frequency response test, we know that they couldn't operate at a viable frequency on par with the desired movement response of the bicopter pitch controls. The data collected from these tests resulted in a swap for a larger and more robust positional servo motor, the NG995. However, the only way to check whether these new servos would make a difference was to tune the bicopter and calibrate it. But without seeing it flying in the air, one could not tell how to modify the parameters just by looking at it. That's where the attitude test rig came in. By mounting the drone on a single movable point, the drone's movement could be isolated and tested to reach a desired stability in its flight. The parameters that had to be changed specifically were PID values and gyrometer and accelerometer parameters. This tuning was done for over a week, as this process constantly demanded new approaches to flight tuning. At the end of this tuning process, I had produced a bicopter that could fly semi-stable on a test rig anchored to the ground. But the real test of success was whether this drone could be flown in the air, how stable it could fly under outdoor wind and air currents, and how long it could remain in the air for. We had a flight day to test this drone outdoors under these conditions. By beginning flight protocols on this drone, we could instantly get it in the air, bring it down or let it crash, and reset it for another test. We completed 6 tests in total. The results of this research split into 2 sections. On one hand, this research extensively documented an ordinary SG90 servo motor, a hobby servo motor, used in many contexts of robotics research. I successfully came up with a framework for diagnosing the problems that come with the intense use of these servo motors, giving undergraduate and graduate student researchers another avenue to understand positional servo motor hardware. On the other hand, those results, and the results of extensive attitude testing and PID tuning, led to the longest observed flight for the IDCL bi-copter, with increased maneuverability and responses that exceeded the expectations of this research. Thank you for listening to the breakdown of the research that I did at the Schulich School of Engineering this summer. Once again, I'd like to thank Dr. Bishaban for sponsoring this research project.